Can you guys hear me?
Yes.
Okay, we might wait a minute or two after 11 just so that people have enough time to join. If what you can do in the meantime before we actually get started, if you go into your module 4, there is a worksheet that we're going to do on the document camera today. So that's under the module 4 lecture screencast. It's called Radical Halogenation. So you might want to download that PDF. Then there's also a table from your book about bond dissociation energies. So it looks like that. So we're going to be using those two things today. So I think we'll go ahead and get started. So again, the reason I wanted to move over to Zoom is because I can share the document camera and it can show to the main screen as one of the comments on the stop, start, continue. Let me just share this as well. Hopefully you can see this canvas shell here for module 4. So module 4 is on radical and ionic reaction mechanisms. So that's the actual, we're getting down to the nitty gritty of organic chemistry where we start learning reactions. So we've learned a lot about what functional groups are, what physical properties they impart on matter. Now we're going to learn how you transform one functional group into another. And so those are the reactions. And they happen two ways, either through a radical mechanism or an ionic mechanism. Ionic basically means that two electrons are moving and forming the bond. Radical means one electron is moving. So in this module, we're going to do chapters 6, 10, and 7 in that order. Chapter 6 is really spread out amongst chapter 10 and 7. So I'm not specifically covering chapter 6 by itself because it's easier to understand that in the context of the reactions. So we'll disperse that information amongst 10 and 7. I'll show you the reason why we're going to learn chapter 10 first before chapter 7, and I hope you understand the logic behind that. So here is, I think I have yet to populate that, but so there's some screencasts. These chat recordings will be stored here. Your chapter readings are these links. Then you have 6, 10, and 7 homework sets. Now keep in mind, there's no Orions. The feedback was people did not like the Orion. They found it redundant. So the associated Orions have been folded into the homeworks in terms of the points. So now each homework set is worth 20 points rather than 10 points. So I strongly encourage you. We're on the downhill slide of this semester now to start doing these homework sets early and often. They are due at 11 a.m. and that's my policy. It's 11 a.m. is not 11:59 p.m. And the reason for that is if we were meeting face to face, they would be due the day of the exam, and that's always been my policy. And so I would say do them early and don't wait. So that's sort of the change in Canvas there. Any questions before we get into the lecture? So let me, I guess, let me show that, where that actually is. I can't tell if you can see that or not. I don't think you can. Okay, so I think you can see this now. So if you go to Module 4, Lecture Screencasts, the Radical Halogenation worksheet, the first page looks like this. Then the homolytic bond association energies, it's one table from your book. It's table 6.1, it looks like that. So those are in the lecture screencasts of Module 4. I think someone said you could go to files as well. I don't do that too often, but maybe we go to modified. Yeah, you can see them right there. We'll be using those two today. So pardon my Zoom ignorance. I don't use it often. But let's go ahead and get started. So can everyone see this slide that's presented now? It says think, pair, share. So what I want you to do is take a few minutes. And if you want, you can unmute yourself or you can type in the chat. Either way is fine. So I want you to consider the following prompt. Take the first 3 alkanes, methane, ethane, and propane. And without knowing how this happens, what I want you to do is substitute 1 hydrogen atom for 1 chlorine atom in each of those types of alkanes. So over the course of chapter 10, we're going to learn about how that actually happens. But the big thing I want you to do now is just take the alkane, make the monochlorinated alkane. For each of those, write down the structure, compare the starting molecular formula to the final molecular formula. Look at the mass change. What's the mass of each molecular formula? How many carbons atoms does each have in the starting material and the product? How do you think the C13 chemical shift differs? The big thing for this chapter is how many unique sets of hydrogens are you starting with? What is the hydrogen ratio in each set? And then if you consider the the proton NMR, how does the chlorine atom influence the chemical shift of the hydrogens? And then the big thing is what is the probability of each type of unique hydrogen atom being substituted. So I want you to think about that before I actually tell you what that means. So let's take 10 minutes or so to consider this. If you have questions, again, you can unmute or write them in the chat. So I really want you to think about that before I start writing stuff down. Does anyone know how you shut the beep off? I do not. It sounds like a doorbell every time someone enters the Zoom meeting here. So again, if you just joined us, we're considering this prompt where you take the first three alkanes, methane, ethane, propane, and you're substituting a hydrogen atom for a chlorine. At this point, we're not considering the mechanism of how that happens. We're just considering what the product is and comparing them with these prompts here. So write down the structure, determine the molecular formula, determine the mass, unique number of carbons, how does the halogen affect the carbon shift, unique sets of hydrogens, what's the hydrogen ratio in each, how does the halogen affect the hydrogen peak shifts, and then finally, what is the probability in the starting material of each unique hydrogen being substituted. So maybe in the chat, or you can hold up to your camera. I can only see so many people in the little camera box here. Maybe what you can do is show what you wrote down for methane. Or in the chat. So Carla, you might want to consider your molecular formula for methane again. So what else do we know about chlorine? So Aiden says the mass goes from 16 in methane to 50 in methyl chloride or chloromethane. What do we know from mass spec of halogens? What also will the chlorine atom do? So Aiden wrote down the mass for for one isotope of chlorine. What would be the mass if we considered the other isotope as well? So yeah, the chlorine, remember, it has a natural abundance of 3 to 1 of 35 to 37. So you're going to observe that in the parent region. So let me show you what I did for methane. Now what? All right, there we go. So can everyone see the document camera? I'm getting some nods, it looks like. I feel like I'm in the war room looking at all the different generals reporting back to me. Someone says it's blurry. Hit the old autofocus. Is that in focus now? Okay, so if we take methane CH4, the molecular weight is 16 grams per mole. That's just 12 plus 4 times 1. That's how we get 16. For the unique number and sets of hydrogen atom, there's only one type in a ratio of 4. There's only one type of carbon. The blue is the chemical shift of the carbon atom, so 1 part per million. The brown, burgundy, whatever you want to call that, is the chemical shift of the proton. It's 0.23. So what we are doing, what this question is asking you to do is substitute 1 hydrogen for 1 chlorine. So I want you to understand what that means, because we're going to use that word a lot. Substitution. So we are substituting one element for another. The substitution we happen to be doing is called CH substitution, and that's the basis for chapter 10, which is radical reactions. So we've substituted an H for a chlorine. Now this gets us a molecular weight of 50 if we're just considering the 35 Cl, but if we consider the 37, it's 52. And again, there's our ratio 3 to 1. So that's what you would expect to see in the parent region of the mass spec. So now the same thing for here. There's one unique type of hydrogen. There's 3 of them. There's one unique carbon. So notice the chemical shifts now. That substitution of H for chlorine has moved that chemical shift quite a bit. This is electronegative. You're pushing it away from 0. You're now at about 26 in the carbon. You're now at 3 in the proton. So this is the experimental data that you will observe to confirm the structure of that product. Any questions on methane? So really what we're doing now is sort of what physicists call a thought experiment. It's basically, we're using all the knowledge we have in synthesizing data. So where did this 52 come from? Remember that the chlorine element exists as two isotopes in a ratio of 3 to 1. So when you encounter chlorine in nature, there's chlorine 35 and chlorine 37. So remember, these are isotopes of one another. When you incorporate chlorine 35 into this molecular formula, the molecular weight is 50. Chlorine 37 into this molecular formula is 52. And you will see a ratio of 3 to 1 in the parent. So remember what that means. If that's your 3, then this is sort of your 1, 3 to 1. So let me ask you some questions about ethane. So I just want to be clear. Everyone can see this document camera like in big, right? It's not tiny. So ethane. What how many unique H sets are there in ethane? What's the ratio of them? These parent masses occur together, meaning if you run this experiment with this compound, you see both of these masses. So if you take ethane and you do a CH substitution for chlorine, how many different products can you get? So you get 1. What's the name of that product? We might as well review some nomenclature while we're at it. So chloroethane. So the mass spec you're seeing again, you're seeing both of these 50 and 52. M over Z is mass to charge. So Z is equal to 1, so you're really just seeing the mass. You're seeing both of these. I only wrote down the molecular weight of this one. Blakely, does that answer your question? The unit is the atomic mass unit. You can think of this as the parent, and then you can think of this as M plus 2. But they are both occurring in the parent region because they have the fully intact molecular ion. So here's the data for ethane. So the mass spec is telling you molecular weight in a sense, right? So weight is a phenomenon due to gravity. Mass is a phenomenon associated with the intrinsic property of the element itself. So in chemistry, we sort of use both terms colloquially, meaning we don't really split hairs on that. But In the mass spec, we're using atomic mass units, which we sort of just assume is grams per mole, if you want to think of it that way. So here's our response for ethane. So we did the same thing. 2 times 12 is 24, plus 6 times 1, that gets us your 30. There's only one unique type of hydrogen set that integrates to 3. They occur at a chemical shift of about 0.86 parts per million. There's one unique carbon at 6.5 parts per million in that spectrum. We're substituting an H for a chlorine. Now, in the parent region, we do the same thing. We have the 3-to-1 ratio. All I've written here is those molecular formulas with 35 and the 37. So that gets you 64 and 66, again, in the 3-to-1 ratio. Notice how the chemical shifts change. We started at 6.5. The carbon bearing the chlorine now shifts quite a bit to about 40. This one shifts a little bit more. And the reason this one shifts is induction. So remember, induction is through bond. Induction is through sigma bond. Resonance, which we do not have here, is through the pi bonds. So those two things explain quite a bit. But the reason that you don't see a big shift on this one is because it's further away from the halogen. But the reason it does shift is through induction. So notice now when we did that substitution of H for chlorine, now we have 2 sets that integrate 3-to-2. That's the ratio. We end up with the 2 carbons as we've seen. So I talked about probability. There's 6 hydrogens here, right? The probability of substituting one of them is 100% because they're all the same, correct? Does everyone buy that? Aiden's showing the thumbs up. Okay, now propane. So we don't want to walk off a cliff and make assumptions that we did. So look at propane, and I want you to now take a couple minutes and consider the same type of example, same thought process, but for propane. It's going to change a little bit, I'll tell you that. And I'd like some feedback either through the audio or the chat explaining why it changes. So Rosemary's asking to repeat the question. So remember, from the start of this semester, I've been asking you guys, when you look at a compound, and I'm asking you to determine the unique sets of hydrogen. Now that comes into play for propane. Methane and ethane only have one set. How many unique sets of hydrogen does propane have? So it has 2. What is the ratio of those sets? So 6-to-2 or 3-to-1. Now that is the crux of chapter 10. This is where, so you saw how that was important for NMR, right? Where you saw these signals occurring at different spaces because they were different chemical shifts because they were unique. Now what we are talking about in terms of uniqueness is the reactivity of those unique type of hydrogens. And that is crucial to chapter 10, because when you take an alkane and you do a CH substitution on it, you will know rationally where that substitution occurs. You're not throwing a dart at a board and it ends up anywhere. You're using what you know in terms of organic chemistry to say, if I use this specific halogen, the substitution is happening at this specific part of the molecule. So when you take propane and you do a monochlorination, how many possible products can you end up with? What are the names of those products? So 1-chloropropane and 2-chloropropane. Now what I want you to do for each of those is the same thing. Is basically for each one, how many unique sets of hydrogen do you get? In the ratio, how many unique types of carbon do you get? And can you use that information to differentiate those two products? So for 1-chloropropane, how many unique types of hydrogen do you end up with, and what are the ratio of those hydrogens to each other? Yes, this chat session is being recorded. It will be uploaded into YouTube and linked into Canvas. So yeah, you have 3 unique sets in a ratio of 3 to 2 to 2. If you do the same thing for 2-chloropropane, Ian has done that as well. There's 2 unique sets, so we have some debate between Ian and Rosemary about the ratio. So maybe we want to get some other contributions about what the ratio should be. Seeing some 6 to 1s, that looks about correct to me. So let's go ahead and sort of review that now as well. So what are we considering? Again, here is, and for these, in some sense, it's sort of easier to draw things out like this rather than the bond line, because this allows you to really just explicitly count those hydrogens. So here's propane. It's 44 grams per mole. We have 2 unique type of carbon. They're shown here. You have methyl groups and methylene. They sort of cluster one another about 16. We have 2 unique type of hydrogen shown in burgundy. The methyls are at about 0.9 parts per million. The methylene's at 1.2 parts per million. And we have the ratio of 6 to 2 or 3 to 1. remember when we said we use this classification scheme? So we're gonna use this quite a bit as well. So primary we can call primary methyl, secondary methylene, or tertiary methine. We're going to use that quite a bit in chapter 10. So if we substitute a primary H or a methyl H, this is what we get, 1-chloropropane. The mass changes to 78. The carbon chemical shifts now change. The carbon bearing the halogen is about 46. Again, as you move away from that halogen, these chemical shifts decrease. The same thing in burgundy here. The hydrogens of the carbon bearing the halogen are about 3.5. We move out the methylenes 1.75. Further out, the methyl is 1.05. You're still seeing your 3-to-1 ratio. So this was for substitution of a primary, but we can also get substitution of a secondary. So notice that the mass does not change. This is just a constitutional isomer here. The mass stays the same, so you really can't differentiate off that. What you can differentiate off now is basically the proton and carbon data. So now you have two unique type of hydrogen sets, 1, 2, and a ratio of 6-to-1. You have 1, 2 unique type of carbon. So you can compare your spectral data, this data to differentiate the constitutional isomers. So that's what we learned in the second module with spectroscopy. Are we on the same page with this logic so far, or do we need another run through of that? So now I want to ask you a question. We said if we look at our starting ethane, Blakely has a question, the video closed. Can everyone still see this? What do you mean by the video closed? So here are again, we're considering our starting material, propane. We said there are two unique sets, the ratio of 6-to-2. Now, all I'm doing here is the 6, 3, 6, those come from methyl groups. Those are primary, correct? The 2 comes from the methylene. Those are secondary. Now what I want you to calculate, it's pretty straightforward. What's the percent contribution of each of these to the total? So the primary hydrogens, what percent contribution of the total number of hydrogens is that? Mac and Aiden need to duel it out. Someone needs to throw up another number. Okay, we have some consensus now. So 75-25. Put another way, what's the ratio between those two? If you just sort of condense that down to a ratio, what's the ratio? So 3-to-1. So this is what we're doing right now. We're talking about the probability. If we were to run this reaction taking propane and making monochlorinated propane isomers, what is the probability of the product distribution? We already classified the primary versus secondary. We had 6-to-2 for a total of 8. The contribution of those 6 over 8 is 75. Of the secondary, which are 2 over 8 is 25. That gives you a ratio of 3-to-1. Now, what are we doing with this piece of logic? Again, it's a thought experiment. If you think about taking propane, you mix it with some chlorine gas, you run the reaction, and you're able to isolate the products, you would expect 75% of that product distribution to come from substitution of the primary. 25% from substitution of the secondary, yes? Is purely based on the counting and the arithmetic. So if things were that easy, which they're not, everyone would get an A, and this would be a happy life. So if you actually run this reaction, the product distribution is the following. The primary hydrogens are substituted 45% of the time. The secondary hydrogens are substituted 55% of the time. Now notice, this is what we want to learn and to explain. This is what you expect. This is what you observe. The ratio between these two, this and this, it's now 1 to 1.2. All I did was take 45 divided by itself to get 1, 55 divided by 45 to get 1.2. Again, this is just a separate way of considering what we expect with what we observe. Now, this new thing is this next sort of column I'm going to show you. This is going to be new to you, and I'll explain it. It's not anything terribly complicated, but it's going to get to helping us understand why we do not observe the expected ratio. So why? So this last column here is called relative reactivity. I'm taking the observed percent, I'm dividing that by 6. 45 divided by 6 is 7.5. Taking the observed percent here, 55 divided by 2, that gets you 27.5. Now when I take that ratio, the secondaries divided by the primaries, 27.5 divided by 7.5, I get this number here, 3.7. What this number is telling you, the secondary hydrogen is 3.7 times more reactive than the primary hydrogen. Does everyone follow the logic so far? So again, the big picture of this, when you consider an alkane, you have carbon-carbon, carbon-hydrogen bonds. There's not much you can do to an alkane to functionalize it other than what we are going to learn in chapter 10, where we substitute an H for a halogen. But we want to be very rational in understanding when we have different types of hydrogens, which one gets substituted. So that's what we're aiming to do. So we want to understand, why is this? Why do we get more substitution here than we do here when we have this existing ratio? So any questions on this before we sort of move into the worksheet? Blakely, what's your question? So just to recap this, when you're looking at an alkane, you classify the types of hydrogens. In this one, we have primary and we have secondary. So we noted that primary, secondary, we counted them, 3, 3, 6. The secondaries, we have 2. If we were to substitute either of those for a halogen, this is the ratio we would expect. 6/8, 75, 2/8, 25. That's just a thought experiment of what you would expect without knowing anything else. In reality, these are the numbers that you observe. The ratio of this is 1 to 1.2. This relative reactivity number is taking the actual percent you isolate divided by how many of that type there are to get you these numbers here. Now, this ratio of secondary to primary tells you that the secondary hydrogens are more reactive than the primary. And this is how we rationalize what type of hydrogen gets substituted when we do a radical reaction. But why is that? So let's look at our worksheet. And let me ask another question. Do you guys only see the document camera now, or can you still see my slide deck? So you only see the document camera. So if you can, either open your book, this is table 6.1, or download this PDF, because these are the numbers that we're going to use to fill in this table. This worksheet that we're going to go through, basically, it covers all of chapter 10. It has elements of chapter 6 in it, which talk about Gibbs free energy, as well as reaction coordinate diagrams. So even though this says chapter 10.1, this is from the old textbook, it's 6.1. This worksheet is going to lead you through some very basic exercises for understanding why the different types of hydrogens get abstracted. So first things first, find the delta H values for CH homolysis of the following molecules. So this term here, delta H, what does that mean? Do you remember from Gen Chem? So that's the enthalpy. So it says CH homolysis Do we know what homolysis means? So yeah, it has to do with bonding. So lysis means cleavage. Homo means same, so same cleavage. What do we mean by homolysis of this type of bond? So there was some confusion in Wiley Plus about arrows as well. If we're considering this bond and we want to break it homolytically, same cleavage, that means each element gets an electron. There's 2 electrons in this bond, correct? So if we want to show that with arrows, we use the fishhook arrow. The fishhook only has one sort of head to it, right? That indicates the movement of 1 electron. So there's 2 electrons. Each element is getting an electron in that bond. So that's what it means for homolytic cleavage. So that's what these numbers here are. So the first one, methane, CH3H. Remember we said there's only one type of CH bond in methane. We go over to our table, bonds to H. There it is. Now, I really want you guys to only consider kilojoules per mole. So what we're going to write there is 435. So now it says ethane. Remember, we said there was only one type. 410. So I'm looking at this. The table is a smidge incomplete, I might say. Okay, we'll just run with these numbers. I have a different table. The other table has a little bit more examples on it. So the next example for propane, remember we said there were 2 types. I'm going to say H secondary, H primary. I don't really see the propane primary on here, so we're just going to assume that it's the same as this one right here, the ethane. So we're going to put 410 there. This next example here, this is the secondary cleavage for propane. Again, you have to get used to how this condensed thing is drawn. This is propane, and what they're showing you is the secondary hydrogen. So this is 397. This next one, 2-methylpropane. There's propane. There's 2-methylpropane. Then it says the tertiary hydrogen. So it's this hydrogen here. And that is this one right there in the next next row of that column. So that's 381. Looking at these numbers, can you see a trend? If so, can you explain that trend to me? So Max says the delta H values get smaller as you increase the number of carbons. So yeah, basically methane to ethane. And if we look here, primary versus secondary, what this number is telling you, remember what enthalpy means and what this homolysis means. If you want to cleave this bond right here, this CH bond, if you want to cleave that, you have to put in 410 kilojoules per mole of energy to cleave that homolytically. This one right here, the secondary CH bond, if you want to cleave that, you have to put in 397. Now, considering this logic here, we said secondary was 3.7 times more reactive than primary. Does this make sense with these numbers? So Rosemary just sort of answered that. So yeah, you think about you have this molecule and you are applying, say you have like a blowtorch. You're applying heat to this molecule. Say you're starting at whatever, 0 kilojoules per mole. And as you apply heat to this molecule, what number do you hit first? You hit 397 before you hit 410. So the fact that you hit 397 kilojoules per mole first means you are preferentially cleaving this bond before that bond. So secondary is cleaved before primary. And sort of like the reason we saw with pKa's, the thing you're forming is more stable. You're able to cleave this greater than that. Because you're forming these things here. You're forming a secondary radical versus a primary radical. So the radical stability also plays a role as well. So now look here, 2-methyl propane. This was tertiary, right? This one's even lower. If you cleave that, you form a tertiary radical. And again, you classify radicals by counting the number of carbon groups. This carbon here is bearing the radical, so you have 1, 2, 3. It's tertiary. So our radical stability trend, tertiary is greater than secondary, which is greater than primary. So whenever you're doing this type of problem and you're asked which hydrogen gets substituted, that's the order in which you do it. So we have 2 minutes left, and I want to ask you another question. But I encourage you to go through this worksheet, try to fill out as much as you can, and we'll continue to do it over the course of our lectures here. But let me switch over to the slide deck so I can ask you a question. Hopefully you can see that prompt. Consider the C4 hydrocarbon butane. Consider substituting one hydrogen for one chlorine. How many possible monochlorinated butanes are there? I think if you squint, you can see the next slide in the slide deck and probably get the right answer. I can understand why you would pick 2 because butane has 2 unique sets of hydrogen, correct? No, you're only considering the linear butane. So just the linear isomer of butane, C4. So butane has 2 unique sets of hydrogen, right, in a ratio of 6:4. The answer is not 2. The answer is 3. Can you think of a reason why it's 3? So what I want you to do is draw out, for your initial 2, draw out those 2 structures right now. One of them has something unique about it. What is unique about it? Again, just because we finished module 3 doesn't mean you can flush that information down the mental toilet. You still have to retain it. What's the names of your 2 initial products? What are their names? So 1-chlorobutane and 2-chlorobutane. What is special about 2-chlorobutane? So consider the next thing. I know we're a little bit out of time, but which of the following correctly names the 3 monochlorinated isomers of butane? So yeah, the correct answer is C. Again, what is now what's the twist on this? Your first approximation you came up with 2 sets, right? You had your primary methyls and then your secondary methylenes. Then you thought there can only be 2 products. But in reality, you can get 3. And the reason you can get 3 is because when you substitute at the secondary position, you end up with R and S. So what we aim to do over chapter 10 is understand why can you get R and S? And that has to deal with the geometry of a radical itself. So we'll pick that up on Wednesday. I encourage you to start doing your homework sets. Again, the homework sets are now worth 20 points. try to get to them as soon as you can. If you have questions, shoot me an email, but hopefully this Zoom thing worked out all right. We'll continue to use that. Other than that, I think I'm going to go ahead and shut it down, and we'll see you Wednesday. All right, take care.